Hi, welcome. This is the 20th session on measure theory, and this is the second session on Lebesgue integral. So what we are going to do today is, it's a third session on Lebesgue integral. I was a little confused. And in the last session, we introduced the monotone convergence theorem, stated it without proof, and we explained why it's important. Today we are going to give a proof, and we will give a few applications, beautiful applications of them. Already we saw one application yesterday, right? So let us get started. So what did monotone convergence theorem say? Let me just check everything is all right. Yeah. So we are starting with a measurable space, measure space. Okay. And Fn a sequence of measurable functions, non-negative. And our assumption is Fn's are increasing sequence. What does that mean? For all x in, for all n and for all x in x, Fn of x is less than or equal to Fn plus 1 of x. Notice that these are all real valued, therefore this makes sense. Okay, right. So what does the theorem say? The theorem says that integral of Fn, then conclusion is integral of Fn increases to integral of f. In fact, that is, notice that by monotonicity, okay, do you understand this theorem? This is the monotone convergence theorem. So let me call it MCT. This is a short-term notation. Throughout the course, I will be using. MCT stands for monotone convergence theorem. As I said, even though the word is monotone, this is actually increasing. It deals only with increasing sequence. Please remember that. We will look at it, a counterexample later. Okay? The few things we should notice. Note, since Fn increases to f, okay, Fn is less than or equal to f. Then by monotonicity, which we already proved integral of Fn, as I said, whenever I write integral of Fn, etc., it means integral of Fn du mu with respect to x. Okay, I will use only the shorter notation. By monotonicity, this is always true. Okay. And second thing is, remember that my integral Fn, integral f could possibly be infinity. Okay, right. We are not ruling out any of these things, right? Okay. So, and since it is increasing, integral Fn is an increasing sequence of in positive real numbers, non-negative real numbers, right? Therefore, its LUB always exists. Okay. So either the LUB of this set integral Fn is infinity or it's some real number, positive real number, doesn't matter, right? So what we want to, therefore when we want to show integral Fn increases to integral f, what does it mean then? Therefore it says limit of integral Fn equals integral of f, right? Since this is an increasing sequence, its limit is LUB, right? Therefore, what we have to show, by monotonicity, I know integral Fn is less than or equal to integral f for all n. Therefore, this means integral f is an upper bound for the set. Right? Therefore, the limit of integral Fn will be less than or equal to integral f. Okay? Please understand that we are doing little analysis. Okay, it's not just like that you are writing. You should understand what it means. First, I have to say what the limit exists in the extended real number system, and the limit is the supremum or LUB. And then we are saying this is already an upper bound for each of the thing, therefore its LUB must be less than or equal to b. Okay, pause, review, proceed. Okay, so we need to prove the reverse inequality. What is it? It is, we want to say limit integral f n is greater than or equal to integral f. This is what to prove. Right? Now comes the interesting thing. Remember, integral of f, we didn't define it directly. Integral of f was defined as the LUB or supremum of integral of s, okay, where 0 less than or equal to s less than or equal to f. Of course, s is a simple function, so I don't want to write this one. Okay, s is a simple function. Is that clear? So if I want to show this is less than or equal to integral of f, that means this whatever this number, extended real number, is greater than or equal to LU, least upper bound. In particular, this limit integral f n must be an upper bound for integral s as 0 less than or equal to s less than or equal to f and s less and s plus for this set. Okay, if this statement is true, then this must happen, right? So the idea to prove this fellow, this pinkish thing, let me call it pink box, okay, this pink, okay, is to show, therefore plan is to show, okay, limit integral n is greater than or equal to integral for any s and s plus with 0 less than or equal to s less than or equal to f. That means this is an upper bound for each of the elements in this set. Okay, if you want to make it again, this is set greenish. So this fellow is an upper bound for the green set. Yeah, okay. So understand this. Now there is again another twist. This is the trick now. Okay. So we have to prove that this also we don't prove directly. The trick is you fix a real number c between 0 and 1. We shall show that limit integral f n is greater than or equal to c times integral of s, where s is as above. Where s is a positive simple function, non-negative simple function, which is less than or equal to f. Okay, and since this is true, okay, and since this is true for every f, true for all c 0 less than c less than 1, it follows that limit integral f n is greater than or equal to integral f's. Is that clear? So pause, review, proceed. So notice that is the important trick in the thing. Okay, the rest of the things arguments are very easy. Okay, so I want to say limit integral f n is greater than or equal to integral of f, right? But integral of f is not directly given. It is given as the LUB of integral of s with s, whatever the conditions are. So we have to prove limit integral f n is greater than or equal to integral of s. But that also we don't show. We show it only is greater than or equal to c times integral of s, for where c is any arbitrary real number such that 0 less than c less than 1. That is the trick. Okay, please understand that. The second trick we are going to use Remember, for any simple function s, we introduce a measure mu suffix s, mu sub s. Do you remember that? And what did you prove? If en's are measurable, en increase to e, then mu s of en naturally will increase to mu s of e, because mu s is a measure. That fact also we are going to use. Okay, these are, there is one trick, there is another important tool. Okay, let us go back, get the job done. So let s be in s plus b such that 0 less than or equal to s less than or equal to f, number 1. Let 0 less than c less than 1 be, okay, let this be fixed. Okay, right. Now once it is done, I want to define increasing set, the set x in x, so that let us look at, see, now I know yes, s of x is less than or equal to f x. There may be equality, but if c is strictly less than 1, you see that c times sx will be strictly less than fx. Therefore, the picture will be something like c times sx into fx. You understand that? Right. Now, what is that I know? Okay, I know that my the sequence fn increases to f. Right? Therefore, that means this is pointwise. Okay, this means fn of x increases to fx. Therefore, after certain stage, okay, let us look at this interval. If you want to think of this, look at this interval, cs of x, f of x, plus some thing, okay. Now it's increasing, right? I don't care what epsilon you want to put, take it anything, okay. But fn of x is always less than or equal to fx, therefore it will be actually here. Do you understand that? My fn has to be here. For if n is large, this means fn sufficiently large. Okay, fn of x has to increase fx, therefore it has to be here. Do you follow that? So what I mean to say is this. Therefore, en set of x in capital X, so that fn of x is greater than c times s of x. Now notice that c is fixed, s is fixed. They are not allowed to vary now. Yeah. So what did I show is, so we claim now what I did here actually says this is en, and next is ens are increasing. Therefore en increases to x. These are what we want to claim. First notice that en is contained in en plus 1. That is very easy, because fn plus 1 of x is greater than or equal to fn of x, and if my x belong to en, then fn of x is greater than c of s of x. Therefore fn plus 1 also belong to this. Right? This shows that if x is in en, x is in en plus 1. So pause, review, proceed. Next thing is I want to claim union. En is x. That is also clear. If x is in x, as I said, fn of x increases to f of x, and csx is strictly less than f of x. Therefore, look at this interval, csx and the close to fx. Okay, since fn increases by convergence of sequence, there is an n, call it n naught, for the given x, so that fn naught of x must lie here. For all n greater than equal to n naught, fn of x must lie here. Right? Therefore, this is also clear. So what you have shown, let us recall, what is en? En is set of x in capital X. Remember this picture so that you will know that my fn of x has to be here. Okay, so that fn of x is strictly greater than c of sx. Okay. So what we have proved this en is increasing to all of x. And by definition, these are all measurable, obviously. Right? Therefore, what we know is Since S is fixed, then we have the mu s. This is the associated measure which we saw in the last session. Right? Therefore, I know mu s of En should increase to mu s of x. That is for abstract measure theory. We had already proved it. Property of abstract measure. If mu is any measure and my Ens are all measurable and En increases to E, then mu of En increase to mu of E. Okay. So this happens. This is the tool which you are going to use now. So let us look at integral of Fn now. Integral of Fn, this is all over x. This is certainly greater than or equal to integral of Fn over En. Why? Notice that this by definition is, why is this true? Because integral of Fn over En by definition is integral of Fn integrated function of En over x. Right? Now Fn is greater than or equal to Fn of integrated function of En of x. En. Right? Therefore, monotonicity of the integral, this is clear. Okay? Okay. Sure? This is a small PRP just to make sure. Once you have this kind of complete understanding, you will see that the thing. Now, on Fn, on En, what is the role of Fn? Remember, how did you define En? En is set of x so that Fn of x is greater than or equal to c times sx. Therefore, this means this integral is greater than or equal to Fn is greater than or equal to c times Fn on En. Fn is greater than or equal to c times s of x. Therefore, again by monotonicity, this is greater than or equal to c times sx. X d mu x if you want to write. Okay, c times s. Is that clear? Yeah. But notice that this by homogeneity, positive homogeneity. What does that mean? If S is simple, non-negative, okay, S belongs to S plus, and C is positive, then integral of CS we had already proved, integral of C into integral of S. I am using that. Therefore, this is C into S over En. Yeah. So, what you have proved is, one is integral of N is greater than or equal to C times integral of S over En for any N. Okay. Pause. Review. Proceed. Now take limit. But notice that before I take limit, let me see. Therefore, integral of Fn is greater than or equal to C times integral of S over En. But this is C times mu s of En. Right? Therefore, by taking limit, we see that limit of integral Fn is greater than or equal to C times limit of mu s of En. But this is equal to C times mu s of x because En increases to x. But this by definition is C times s over x. Yeah. Therefore, you have shown limit of integral Sn is greater than or equal to C times integral of s. Wow. Major goal achieved. The tricky part is achieved already. So, therefore, as we, sorry, this is Fn. Okay, don't think of this. Okay, right. Now, what? Now, since C is one is arbitrary, okay, we obtain limit integral Fn is greater than or equal to integral s. And since s is in s plus in 0 less than or equal to s is arbitrary, this shows that limit integral Fn is and upper bound for this set. Integral s 0 less than equal to s less than equal to f, s is in s plus. Hence, limit integral f is greater than equal to limit integral f. So, we already had noticed this is greater than equal to limit integral f1. Therefore, theorem proved. This is one of the very beautiful proofs. Okay, look at the kind of ideas you have to use, and also there is a trick. Okay, the trick was fix s and fix c. You want to show limit integral f1 is greater than equal to integral s for every s with whatever the criteria. Okay, but that we could not achieve. Okay, since we wanted to use f1 increases to f, so somehow we want to tie up integral f1 and with integral of s. The way to do that was introducing the extra number c. Just go through it once more. Okay, please try to enjoy. Don't enjoy the proof, then you will see you will be able to reconstruct the proof on your own later also. Yeah, that's the fun of learning mathematics thoroughly. Okay, so we have proved the monotone convergence theorem. Please review it once again. Right, enjoy the proof. Now we want to give some applications to that. In fact, this, okay, I will talk about it as I go along. Right, the first application we had already seen. The first applications we had already seen. Suppose f and g are positive non-negative measurable function, then integral of f plus g is integral of f plus integral of g. Okay, before application, as I said it is so wait. Let us observe a quick thing. So immediate corollary of MCT is the following. Let Sn, let f from x to 0 infinity be measurable. Let Sn be such that Sn increases to f pointwise. Then integral Sn converges to integral f. So whatever increasing sequence of simple functions you have taken, you integral of Sn converges to integral f. In particular, if I want to find what is integral of f, it says that I only have to take whatever is a convenient sequence Sn of increasing sequence of simple non-negative functions so that Sn increases to f. The choice is mine. It does not depend upon which Sn. For example, we had already said for any positive non-negative measurable function, there is an increasing sequence of simple functions. Okay, I am not duty bound to take that. I can take any simple function. So in particular, as I said in the last session, this is another way of defining Lebesgue integral. Start with any sequence Sn of simple function which increase to f, then define integral f to be limit integral Sn. This limit exists in the extended real number system. Okay, as I observed just now. Okay, that's a crucial idea. Okay, please understand this. These are the things which are never mentioned in any typical course. In fact, I have seen somebody who said, what is the use of monotone convergence theorem? Okay, one of the very good mathematicians exclaiming, okay, exasperatedly in a class after proving this. Okay, you have to dig. Okay, pause, review, proceed. Do you understand this? Okay, very beautiful thing. I would like to write it as great thing. All right. So the first application, therefore, first applications f and g are non-negative measurable functions. Then integral of f plus g is integral f plus integral g. How do I prove that? Yesterday we proved, in the last session it's proved, but therefore I will quickly go through. Let Sn be in S plus, as that Sn increase to F, and Tn similarly increase to G, where Tn of course in S plus, right? Then Sn plus Tn is again in S plus, right? And Sn plus Tn increase to F plus G, right? Therefore by MCT, integral of Sn plus Tn increases to integral of F plus G, right? By additivity property of integral on positive simple function, this fellow is nothing other than integral Sn plus integral Tn, right? By our assumption, by monotone convergence theorem, integral Sn, okay, that increases to integral F, integral Tn, that increases to integral G, and therefore the sum of this sequence converges to this. But the limit is unique, that means these two are equal. So you proved the additivity. This is one of the very interesting thing many people fail to notice. Okay, in Lebesgue integration, to prove additivity of the integral, even for non-negative measurable functions, I needed a very deep theorem, namely monotone convergence theorem. It doesn't come free. Go back to Riemann integral, it will be easy. Okay, there are other approaches to Lebesgue integration directly, there also to be easy. Okay, but this proof is something very, very special. Please understand, additivity is not free, even for non-negative measurable functions. Now, second application. Okay, see, this is what I could have done earlier when we talked about measurable functions, simple functions, etc. I didn't do that. Okay, let us look at a Dirac measure space. We will specify only R and P of R and Dirac measure situated at 0. What does it mean? D of 0 is 1 if 0 belongs to E, otherwise 0. That's it. That is the measure. Okay, we already proved it is a measure space, right? Now suppose F is a simple function, a simple non-negative function on this space, right? Now I know, therefore F, I can write it as summation some Ci I of A, right? And say that I equal to 1 to n is a measurable partition. Partition of X. This is a standard representation, right? Therefore, what is integral of F? Integral of F by definition, therefore, let me write it, integral of F over R. F is a very ugly notation, d delta naught. D mu is this. By definition is Ci times delta naught of A. Right? Now notice that this is a measure, this is a partition. Therefore, 0 belongs to only one, say A1 without loss of generality. Right? You understand? Therefore, this is going to be C1 into delta naught of A1 plus etc. C2 into delta naught of A2 and so on, Cn delta naught of An. But these are all 0. By our convention, this could be extended real number system, they could be even infinite, but I don't have to worry about. These are all 0. Okay, this is 1. Therefore, it's nothing other than C1. But what is C1? Okay, C1 is nothing other than F of 0. Do you understand that? Hence, if F is a simple function, simple non-negative function on R, P of R, Dirac measure, then integral of F over R, d delta naught is nothing other than F of 0. Okay? Life is so simple, right? I have to compute the integral with respect to this measure. I only have to look at the value of F at 0. Okay? But this is only for simple functions. Now let F be non-negative. Any function is measurable. Do you see that? Because the power set, the sigma algebra is the power set, the any function f from R to R is measurable. So I don't have to keep saying it's a measurable, etc. It's automatic. Right? Now what is the integral of f? Integral of f is LUB of integral of s 0 less than equal to s less than equal to f, and s is in s plus. But this I know it's LUB of s of 0, where s is as above. Right? And notice that s of 0 is less than equal to f of 0. Right? So what all I know is integral of f is less than equal to f of 0. This is all I can conclude at present using this definition. Do you follow this? But Monotone Convergence Theorem comes to my rescue. I know there exists a sequence Sn of simple functions such that Sn increases to f. Therefore, Sn of integral Sn by Monotone Convergence Theorem integral converges by MCT. Integral of Sn converges to integral of f. But integral of Sn is nothing other than Sn of 0. Therefore, it should converge to integral of f. Okay. But remember, Sn of increases to f, that means pointwise Sn of 0 increases to f of 0. Therefore, this actually goes to f of 0. And hence I conclude integral f is f of 0. Isn't it fantastic? Integral f d delta naught over r is f of 0. Pause, review, proceed. Do you find that very interesting? Very beautiful application of MCT. Yeah? There are other ways of directly proving the Dirac measure of any non-negative measurable function, integral of any non-negative measurable function with respect to the Dirac measure at 0 is the value of the function at 0. One can prove it also, but this is a very easy and direct way. Yeah? Very good. And next, a second application. Third application actually. Application 3. Now let's look at our counting measure n, p of n, and let us assume counting measure with weights p. Okay, to recall, what does it mean? Okay, this says that if call this is mu, if mu at singleton n is pn, whereas pn is non-negative. Okay, we will assume pn is 0 at least for some n. Otherwise it will be 0 function, 0 measure always. Okay, therefore if I have something like 179, this set is my E. What is this measure? Mu of E will be P1 plus P7 plus P9. Okay, right. Now what I want to do is I want to find out the simple functions on this measure space, their integrals, and finally the integral of f, where f is non-negative measurable function. This is what our plan is. Right? Now note, so if let us assume f is any simple non-negative function on the space n, p of n, mu, where mu is, and simply write is, okay, counting measure with weights. And Pn equal to 1 for all n, that is simply counting. For example, measure of E here in this E will be 3. That's it. 1, 1, 1. Right? Okay. That is why it's called counting measure. Right. If f is simple, okay, then let me look at when integral of f, what is integral of f? This with respect to this measure over n. Therefore, this by definition is going to be something like Ci indicator function of ai I equal to some amount n, right? So what does this mean? Notice that this simply means I'm going to say ci into summation c1 into summation pi I in e1. And similarly C capital N summation pi I in en. Just to make sure you understand this. Yeah, it's a measure of this fellow is what I have to do. Measure I know is just to sum other pi's, the weights, right? Is this clear? Okay. So in suppose all my pi's are 1, what does that mean? This simply means C1 time number of elements in E1 plus Cn time number of elements in En. Maybe it's easier to write this way. If all my Pn's are 1. Is that clear? Okay. Now, so we had understood what is integral of simple function and their integrals, right? Then I want to know what is the finally f. Now let's assume 0 is less than or equal to s less than or equal to f is non-negative. Again, automatically this will be measurable because my sigma algebra power set of m. Right? Okay. So notice that here this is where the trick comes. Remember, if s is a simple function, I said it is ci indicator function of vi, okay, I equal to 1 to n. Remember, it also said something very interesting, okay, that is if I write si as something like dj indicator function of aj, j equal to 1 to something m, where aj is our pairwise disjoint, okay, then this is same as the integral of s is also equal to summation dj into measure of ej. In this case, it is dj into summation over pj, pi, I running over ej. Make sure you understand this. Okay. So suppose support of yes. Okay. What does it mean? It is set of n in n, so that Sn is not equal to 0. Suppose this is finite. That means the set of n, so that my s of n equal to 0. Okay, its complement is finite. So except for finitely many elements, my Sn is always 0. In that case, you see that integral of s, okay, du mu is nothing other than, I can write it as s1 times indicator function of 1 plus s of 2 times indicator function of 2 plus n times indicator function of n. Where assume that therefore this is a finite, assume this is contained in 1 to n. Right? Some of the s1 s2 sn may be 0 because if my n may be 100, but maybe 1, 10, 20, 20, 21 up to 30, okay, and 91, 97. Maybe these are the only things. Now my Sn is non-zero, but I am saying it is contained in 100. Okay, you see that? Convince yourself this. So what is our assumption? my S of n is 0 for all n greater than or equal to n. Okay, then I am claiming integral of S is nothing other than S1 times P1 plus Sn times Pn. Right? So now suppose you give me an f, a simple function, sorry, non-negative measurable function. Okay, then I can construct a simple function Sn. Okay, Sn of k equal to f of k for 1 less than equal to k less than equal to n. Therefore, my integral Sn is going to be summation pk into s of k, k equal to 1 to n. And notice that my Sn increases to f. By MCT, my integral Sn increases to integral f. But notice that this is nothing other than partial sums of this series. Pn, s of n equal to 1 to infinity. Okay, integral Sns are partial sums. It's a right. Hence, we conclude integral of f over n with respect to d mu is nothing other than okay f of n into p of n. In particular, if mu of n singleton is always 1, integral of f d mu is nothing other than sum of the infinite series. Okay, pause, review, proceed. Please go through that. I had given beautiful applications. They are usually never found in books. Even in our book which you are writing, I forgot to include that I had given us an exercise which I usually do in my classrooms, but I forgot to explain this thing. Okay, it's very beautiful applications. So I hope you don't say what is the use of monotone convergence theorem. You know how useful it is. And not only that, in very abstract, we introduce some abstract measure spaces. Okay, many students learn abstract measure spaces, but they don't learn how to work with integrals over such abstract measure spaces. The two are the important one is Dirac measure and counting measure with weights or plain counting measure. We looked at all those things. We got beautiful results. I hope you enjoyed it. We will meet again. Take care. Stay safe.